Well, it's really interesting to have this connection between the eigenvalue equation and the PageRank algorithm. But in practice, how do you do it, like this connection? And also about the stabilization thingy?
Yeah, these are all really good questions. So in order to figure that out, we have to do a little bit of math first. So let's start off with the initial PageRank vector. And remember, we can just choose this randomly. So I can write this vector, R0, as a linear combination of the eigenvectors that we can calculate of M. So I'm going to write that as A1, V1, and then I'm going to sum that up all the way to A7, because remember, because as you explained to us so well, because the dimension of M is 7, we have 7 eigenvectors at most.
And there.
Thank you. Thank you.
Okay, and from here, how do you calculate the next one? I mean, R1.
Exactly. So we can use our update rule here. So the next vector, R1, is going to simply be M multiplied by R0. Okay, and if I multiply that through, I will get A1 lambda 1 V1, and then summed all the way up to A7 lambda 7 V7.
Okay. And then where do those lambda comes from? How do you get them?
Yeah, that's a really good question. So the lambda ones come from the fact that these V vectors are eigenvectors of the matrix M. So they obey this eigenvalue equation. So we get the lambdas down when we multiply M onto V.
Okay, I think I get it. Let me try to the general formula. So if I understand well, then my vector Rn will be equal to A1 lambda 1 at the power n vector 1 plus plus A7, and then lambda 7 at the power n and the vector 7. Is that right?
Yeah, exactly. That's perfect.
Oh, cool. And how does this help to get the final page rank that we saw in your previous video?
Yeah. Okay. So to do that, we're going to do a little trick where we pull out these two constants to the front of this equation. So I'm going to do that on the next line. So I'm going to take out this factor here. And there's one other special assumption that I'm making, and that is that these eigenvectors, the labeling system is so that we order them in descending size. So that is lambda 1 is the biggest eigenvector, and then the next biggest one is lambda 2, and so on up to lambda 7. So we're also making that assumption. So I'm going to continue here. I'm going to pull out my constant, and I'll write just one more term so that we can see clearly what's going on here. So we have lambda 2 divided by lambda 1 to the power of all to the power of n. And then I also pulled out an a1. So I have a2 divided by a1 and then multiplied by v2. And then I will continue with that up until the last term, which is lambda 7 divided by lambda 1 all to the power of n times a7 over a1 times v7. Yeah, so using the fact that we know lambda 1 is the biggest, we know that these values are all going to be less than 1. And we know if we take a number less than 1 to a large power, that number will vanish. It will just get smaller and smaller the bigger we make n. So it turns out that Rn for very large n is going to be approximately the only term in the sum that will be significant is this v1. So we'll end up with a1 lambda 1 to the n times v1. So as you can see, after many iterations of the algorithm, we've just arrived at a single vector.
Okay, thank you. And could you recap how do we predict the score matrix?
Yeah, so we've done a lot of math, so let's do a quick recap. So the first thing we do is we compute the eigenvectors and the eigenvalues of the M matrix, and then we sort them to find the vector that corresponds to the largest eigenvalue, and that will tell us our final PageRank scores.
Thank you, Amy. So the eigenvalue lambda is the scaling factor that solves this equation. And for example, like lambda, it gives you information about, for example, how your vector could be stretched or compressed. So for example, if lambda is greater than 1, you make your vector bigger. If it's less than 1, you make it stretch. If it's equal to 1, then the vector doesn't change. And then if it's equal to 0, you put like your vector to 0, you like squeeze it. You could also have information about like the orientation. So if lambda is negative, then the orientation change.
I see. And can this equation have multiple eigenvectors, or is it just one?
Actually, yes, it could have like as many as the dimension of m. So for example, here our matrix has 7 rows, so we can have until like 7 eigenvalue.
Okay, that's really interesting. But can you give us just some intuition behind this equation?
Yeah, so here m, it's like a transformation. It could be a rotation. So imagine you rotate.
Okay, let me try it.
And then the eigenvector will be of the vector from your toes to your head.
Okay.
And it will not...
Yeah, I see. So it's the vector running
Yeah.
through me. But then in this case, what is lambda?
Because you don't stretch or like you don't do any transformation, so it will be equal to 1.
But Amandine, this equation seems so simple. Is there not a way that we can predict beforehand what the final PageRank scores are going to be?
Yeah, actually, there is like a cool math tool for it, and we call it the eigenvalue equation. And it's like this. So mv is equal to lambda v.
Okay, that's very interesting. And can you just give us some terminology of this equation?
Yeah, so here m, it's our square matrix here. That is a transformation. It represents a transformation. V, it's a vector that we call it eigenvector. Lambda, it's the scalar associated this vectors from this transformation, and it's called its eigenvalue.
Okay, but what exactly is this eigenvector?
Yeah, you're right. So the eigenvector, it's actually a vector that keep its direction under the transformation.
Okay, and what about the lambda, the eigenvalue?
So lambda, it's the scalar. All of the information about the transformation of m, it's in this lambda. And for example, it also gives you information if your vectors could be stretch or shrink. For example, if lambda is less than 1, then your vector shrink. If lambda is greater than 1, then your vector will be bigger, right? And if it's equal to 1, you keep the same. And if lambda is equal to 0, then you project your vector to 0, so you will just switch it.
Okay, I see.
Also,
Yes?
sorry. And also, I forgot about it. Like lambda also give you information about if it's the orientation. If it's negative, then the direction change to the opposite side.
Can this equation have multiple eigenvectors or just one?
Yes, actually, we can have multiple eigenvectors up until the dimension of the matrix. So here you have 7 rows, so we can have until like 7 eigenvectors.
Okay, I see. But this is a lot of math. Can you give us just some intuition behind this equation?
So, for example, if you have a transformation, let's say m could be a rotation. Could you rotate, Amy?
Okay, let me try it.
Great. So then your vector keep the same direction. So it will be the vectors that start from your toes up till your head. It keep the same direction.
Yeah,
Yep.
I see.
Yeah.
And in this case, what would lambda be though?
Because you don't shrink or stretch, lambda will be equal to 1.